Hello, everybody, and welcome to the lecture for today, March 25th. Today's lecture will be a bit different than what we've done in the past, because today's lecture is just a review lecture. And basically what all I'm going to do today is go through this reference sheet that you can use for exam 2, that's happening this Friday, March 27th. As I said in the announcements, the exam consists of 3 computational problems and 1 proof-based problem, and you can use this reference sheet throughout the exam, either up on your screen or print it out. To receive credit for problems, you will need to show your work even for the computational problems. So you need to explain what theorems you're using to be able to make your computations. So without further ado, we can go into the proof here, or the review sheet here. So the exam covers all of Chapter 1, and Chapter 1 started with this definition of GCD. And really the main thing that we introduced this for, even though this GCD theorem is extremely useful, was to get to the unique prime factorization theorem. We needed all sorts of information about GCDs and divisibilities to be able to prove the unique prime factorization theorem. And so the first crucial definition we introduced was this greatest common divisor, which is the largest number that divides both A and B. And the first main theorem we proved, in fact we proved it during one of the Wednesday problem sessions, was that the GCD is always an integral linear combination of the 2 numbers, and it's the smallest one. And that's what I'm going to call the GCD theorem. So if you want to use this theorem in your proofs, you should cite it as the GCD theorem. And as I said, the next thing we did was define what a prime number was and use the GCD theorem to prove the unique prime factorization theorem. We established many lemmas along the way to be able to get to this point, but the unique prime factorization theorem is probably the most useful theorem about the integers that there is. It's very, very crucial. And this is sort of the basic foundational definitional stuff. This is something that allows us to put something in a convenient form, and these 2 definitions are foundational. This is now abstract, what we move into next, which is congruence classes and modular arithmetic. This is invented as a way to be able to investigate divisibility properties of a number through some sort of auxiliary object, which we call these ZNs. So the ZNs, which are the congruence classes, we proved that we can add and subtract and multiply them. We can't always divide. Division isn't always well defined. But the basic arithmetic operations are. So our formal definition was that A is congruent to B mod n, if and only if the modulus n divides the difference of A and B, which, if you expand this out, is just saying that B is A plus some multiple of n, or vice versa, A is B plus some multiple of n. So it's symmetric, transitive, and what's the last one? Reflexive. So it's an equivalence relation, and the equivalence classes are called congruence classes in this case. So once we understood the main objects and that we could add and subtract and multiply them, which were their own theorems, I suppressed them, but I'm allowing you to just sort of use the addition and subtraction and multiplication of congruence classes without citing the theorems. We wanted to investigate exactly when division could happen, and we called that invertibility. So we said that A is invertible if I can multiply it by some other congruence class to get to 1. And the main thing we showed about invertibility is that it's equivalent to a GCD condition. So if A is coprime with the modulus, then it's invertible. Otherwise, it's a zero divisor, which means that I can find something such that when I multiply it, I get to 0, and both of these things are not 0 themselves, which is sort of very contradictory when we think about the usual arithmetic. Usually, if I take something and the product is 0, x times y equals 0, I know that either x or y had to be 0. So zero divisors are like contradictions to this axiom. This axiom doesn't hold always. It only holds, in fact, for prime moduli. Prime moduli are the only ones without zero divisors. So this was the next main theorem we proved. After that, we sort of wanted to understand, okay, maybe I can't always divide by A, but sometimes I can, even if A doesn't have an inverse. And sort of that's what's happening in this theorem. Notice that if D, which is this GCD, is equal to 1, this always has a solution, because 1 always divides any number. But if the GCD is greater than 1, sometimes I can and sometimes I can't. So this is a problem that may or may not have solutions. And this gives you some information about how many solutions there are and what their congruence classes are. The next theorem we proved was the Chinese remainder theorem. This is sort of similar, except here the coefficient of x is going to be 1, and instead of just one equation, I have a system of equations with different moduli. So I want to be able to get that x, a single number x in Z, is congruent to A modulo 1 modulus and B modulo a second modulus, m and n. And we proved that you can always do this as long as m and n are coprime. And this solution, this number x, is unique modulo m times n. So if I had a different solution, it would differ from the original one by a multiple of m times n. And there are no other solutions. All solutions are of this form. So the Chinese remainder theorem was very important in our proof of Euler's theorem, I think. Yes, exactly. It was very well. It was important in our proof of one of our computational formulas for phi, which I'm asking you to commit to memory. So there are two formulas here that I didn't have the space to put on the page, and you should look at the lecture to see what they are and commit them to memory. So if the last thing we did was now section 1.6 that starts here, was investigate how, again, it's all coming back to whether or not we can divide by elements in a congruence class. So here, an element has an order if I can find some power of that element, which is congruent to 1 modulo n. So the first thing we proved about orders was that an element has an order, so it's if and only if it's invertible. So when I start taking powers of an element, either I get to 1, in which case I'm invertible, or I never get to 1, in which case I'm a zero divisor. It's a very nice theorem. It actually, this one is kind of surprising, at least to me. It was to me when I first saw it. And then we introduced this function phi. Phi was the number of elements which are invertible in Zn, or equivalent the number of elements with an order, or the number of coprime elements to n that are less than n. So there are lots of ways to define phi because all of these conditions are equivalent. And the last thing we proved was Euler's theorem, which tells you something about an order. The order of every invertible element of Zn divides phi of n. So we actually first proved something called Fermat's theorem, which did this only for prime moduli, because for a prime modulus, phi of n is p minus 1. So that's what we proved there. And the reason it's simpler when you have a prime modulus is because every non-zero element is invertible, so you don't need to think too hard about that. But when you're not in a prime moduli, you need to use Euler's theorem, which is the same theorem, just in this more general form, where you take phi of n, which just counts the number of invertible elements. And that is the end of the review. Please study this reference sheet. Use it when you study. Let me know if you have any questions about the contents, or if you need more exercises or anything like that. I look forward to meeting with several of you during the working sessions later this week. And I hope you're all doing well. Thanks, and I'll see you on Friday. Bye-bye.